Hi, and welcome back to our chemistry flipped classroom, where we're continuing our conversations about acids and bases. And today we're jumping into two topics, buffers and titrations. So we're going to address buffers first. So a buffer is a solution that's made of a conjugate pair, a weak acid and its conjugate base. So we're looking for an acid conjugate base pair or a base conjugate acid pair. And they have to be weak. You cannot make a buffer with a strong acid and its conjugate base, or a strong base and its conjugate acid. So buffers are always made with a weak acid and its conjugate base, or a weak base and its conjugate acid. So it's always a conjugate pair. So the purpose of a buffer is that it's really resistant to pH changes, even if a strong acid or base is added. And so we make buffers in the lab on a regular basis in order to keep things at particular pH, at a particular pH. We use them a lot in medical applications because it's important that anything we put into the human body is buffered. Our blood contains a buffering system. So our blood is actually at a pH of 7.35 plus or minus 0.05. And our blood actually relies on two different buffering systems so that it stays at that pH. So remember, anything in a biological setting relies on enzymes for proper functioning. And at pHs, when the pH changes, enzymes denature. And so it's really important that things stay at a particular pH. So that's the role of a buffer, is to keep something at a particular pH, even if you add a strong acid or a strong base. So why does it have to be a weak acid or a weak base and its conjugate? And it really comes down to the fact that a weak acid or a weak base only partially dissociates. So our solution, our buffer solution, is going to contain hydrogen ions, but it's also going to contain the conjugate base, and it's also going to contain the undissociated weak acid. So if we were to take a look at our buffer here beforehand, so we have the acid, our weak acid, hydrofluoric acid in this case, and we have its conjugate base, the fluoride ion. So if we add a bunch of base, a bunch of hydroxide ion to that, it's going to react, rather than reacting with the hydrogen ion or just dissociating in the water, it's going to react with this hydrofluoric acid because it is an acid. It's just not a dissociated acid. And in the process of doing that, it's going to decrease the concentration of hydrofluoric acid, but it's not really going to change the amount of hydrogen ion that's present in the water, because rather than reacting with the hydrogen ion in the solution, it's going to react with that hydrofluoric acid. Or if it reacts with the hydrogen ion, then the hydrofluoric acid is going to dissociate and replace that hydrogen ion. And so when we add that hydroxide to that solution, it doesn't really change the pH. On the other hand, if we added acid to this solution, the acid is going to react with that conjugate base, that fluoride ion, and it's going to form the weak acid, hydrofluoric acid, and water. So again, it's not really going to change the amount of hydrogen ion in solution, so there's going to be very little pH change. So the goal of a buffer is to buffer pH changes, to minimize the effect of adding an acid or a base. In order to do that, we have to have a weak acid and its conjugate base, or a weak base and its conjugate acid. They both have to be present. The best buffers are what we call equimolar, so you have equal amounts of the weak acid and its conjugate base, but even if they're not equimolar, it will still work. So that's a buffer. Now let's jump and talk about titrations. So titrations are a way for us to determine the concentration of some unknown acid or base. So we have to kind of go back and review neutralization reactions. So we remember that when we add an acid to a base, we get water and a salt, not necessarily sodium chloride, but some ionic compound. When we mix hydrochloric acid and sodium hydroxide, we get water and table salt, sodium chloride. But neutralization reactions are always going to be reactions between acid and a base, and they're going to make water and some salt. So when we do a titration, we are using a laboratory procedure to determine the concentration of something whose concentration is unknown. And we're going to use a neutralization to reaction to do that. So we have to have a standard solution. We have to have a solution whose concentration is known. And so we rely on the idea that we reach the equivalence point, and we can tell when we get to the equivalence point because we are using some sort of an indicator, and we're going to talk about those indicators. So the equivalence point is the point where you have equivalent amounts, you've added equivalent amounts of acid and base. So your hydrogen ion concentration equals your hydroxide ion concentration, which means we have water. Okay, so how do we know when we reach that point? Well, we're going to use some sort of an indicator. So our indicator is going to change color when we hit that equivalence point. So if we use something like phenolphthalein, it's clear when it's in an acidic solution, and it is pink when it is basic. So when we just start to see the faintest hint of pink, then we know we have reached that end point and that we have added equal amounts of acid and base, and we can use that and stoichiometry to figure out what the concentration of the unknown was. So in terms of doing a titration, we're going to use this piece of equipment that's called a burette. So a burette has markings on it. It's marked very precisely to the 10th place. So you're going to read it to the 100th place. At the bottom of the burette is this little valve, so you can add the standard drop by drop so that you know exactly how much you've added, and you can determine how much of each of the reactants you used volume wise. And then we're going to use solution stoichiometry to determine what the concentration of the unknown is. So here's our titration curve. pH doesn't change very quickly, and then as we approach that endpoint, it changes really, really, really fast, and then it smooths back out again and stays relatively steady. So our indicator is that thing that changes color at the pH of interest. We're not going to worry too much about pH at the end point. If we have a strong base and a weak acid, it'll be basic at the end point. If it's strong acid, strong base, it'll be neutral at the end point. And if it's strong acid, weak base, it'll be acidic at the end point. And that has to do with the conjugate acids and conjugate bases that are produced. So how do we use this information? How do we use the volume that we learned from the burette and the molarity of the known solution to figure out the molarity of the unknown? Well, stoichiometry. We're going to figure out how many moles of the standardized titrant we used. We're going to figure out how many moles of the unknown that is. We're going to figure out the volume of the unknown that was used, and moles over volume equals molarity. So stoichiometry, we've done this before. So here's our first example. We're asked to find the concentration of hydrochloric acid if 30 milliliters of 0.10 molar sodium hydroxide neutralizes 50 milliliters of hydrochloric acid. So first thing we've got to do is figure out how many moles of sodium hydroxide were used. So we're going to do our stoichiometry problem. We're going to set it up starting with our quantity of sodium hydroxide, which is 30 milliliters or 0.030 liters. We're going to use molarity as our conversion factor, 0.1 moles of sodium hydroxide for 1 liter of sodium hydroxide because it's 0.10 molar. And then we're going to use our molar ratio from our balanced chemical equation, which is 1:1. So when we put all that into our calculator, we find that we have 3 times 10 to the negative third moles of hydrochloric acid. And we want to know what's the molarity. And molarity is moles per liter. So we're going to divide by the liters of hydrochloric acid. So we had 50 milliliters, that's 0.050 liters. And we get that we have 0.060 molar hydrochloric acid. So Stoichiometry to find the moles, divide by the volume, and that gives us molarity. Let's do one more. So here we have a 20 milliliter solution of strontium hydroxide. It's neutralized after 25 milliliters of standardized 0.05 molar hydrochloric acid. And it asks us, what is the concentration of strontium hydroxide? So our given is 25 milliliters. We're going to use molarity as a conversion factor and then a mole ratio. So 0.025 liters multiplied by 0.05 moles per 1 liter. That's the molarity, moles per liter. Then we're going to use our molar ratio from our balanced chemical equation to discover that we have 0.03 moles, whoops, that should say moles of strontium hydroxide. And if we want to find concentration, we actually need to divide those moles by 20 milliliters. So 0.03 moles divided by 0.02 liters is going to give us 1.5 molar. That doesn't seem right. I'm gonna have to go back and check my math again. I think I might have already divided by the 50. So, so we'll go over that one in class. All right, let's see if this one's right. Okay, I know this one works. So how many milliliters of 0.20 molar phosphoric acid are needed to neutralize 55 milliliters of a 0.1 molar solution of sodium hydroxide? So this one is just a simple solution stoichiometry problem. We're starting with our volume of sodium hydroxide, using molarity to convert to moles, and then mole ratio to convert from moles of sodium hydroxide to moles of phosphoric acid, and then molarity again, but this time moles on the bottom, liters on the top. This gives me 0.0092 liters of phosphoric acid, or 9.2 milliliters of phosphoric acid. Okay. As always, I look forward to seeing you in class and answering any questions.